In the previous lesson, we looked at neutralization reactions. We looked at three types of reactions, actually. One of those is the neutralization reaction, which looks like this, where we produce water and a salt. And we're going to look more in detail at the neutralization reaction. Let's take this one for an example. Hydrochloric acid reacts with sodium hydroxide. We have a strong acid reacting with a strong base, and the neutral reactions characteristically produce water and a salt, which forms from the anion from the acid and the cation from the base. So this would be NaCl. Now, this particular reaction will go strongly to completion. So we can say that essentially every mole of hydrochloric acid will react with every mole of sodium hydroxide. So we have a 1:1 ratio here between hydrochloric acid moles and sodium hydroxide moles. Well, this gives us a way to solve some useful problems in chemistry. If we know how much there is of one of these things, we can figure out how much there is of another. So let's say, for instance, I knew that there are 5 moles of NaOH. Well, how many moles then of HCl would there be? Well, since it's a 1:1 ratio, I know there would have to be 5 moles of HCl as well. We could set that up, you can think of that intuitively, set up as a conversion problem. In this case, we would start with the given value, 5 moles of NaOH, and this would be the ratio of 1 mole of the HCl to 1 mole of NaOH. So for every 1 mole of NaOH, there's 1 mole of HCl, and so we see this 1:1 ratio gives us 5 moles of HCl. So we could think of this in different ways. We could just think intuitively, or we could calculate it. As we add more steps to this type of process, the calculations are going to become more useful for us. For instance, we could add another step to this. Maybe we have molarity of NaOH and volume. So if I know, for instance, that I have a, let's say I have a 50 milliliter solution, or I use 50 milliliters of NaOH, and I know that the molarity of NaOH is 1 molar. So I could put these things together and I could figure out how many moles of NaOH I have, which then could be used with the ratio. It would look kind of like this. I have 50 milliliters of NaOH. Now molarity is moles per liter, so I can think of the molarity as 1 mole for every 1 liter. I could do the next step. I'm going to convert the milliliters to liters. That would be for every 1,000 milliliters of NaOH, there's 1 conversion factor of Na. There go from 2 moles of HCl, 1 mole of NaOH, mole of HCl. Figure out the number of moles of HCl. So, key idea here, it all comes back to this ratio. So the key thing is this: neutralization reaction, since we have a reaction that goes to completion, or essentially 2 products, the amount of moles of HCl can be used, or the amount of one thing, the acid or the base, can be used to figure out the amount. We can use these ratios in a very useful way. So let's do a few examples And when we do titrations, we use a tool called a burette. So a burette is a long tool, looks like this. It has marks on the side, and then we usually have whatever we're titrating in a flask. So let's illustrate actually. I have a flask here, and I'm going to put some acid in there. So let's say this was the unknown acid. So what if I didn't know something about this acid? Maybe I don't know the concentration, maybe I don't know how many moles there are. I need to find out something about this acid. Well, I could use a known quantity, which I would put into the burette. So let's say I have acid in here, and it's unknown. I could put a known quantity into this burette of a base, NaOH in this case. But it could be a different base, of course, as well. So we have this reaction here between the acid and the base. And since I know that the acid is going to react with the base in a 1-to-1 ratio, I can use the known concentration of the base to figure out the unknown. So I'm going to put, before I do this, I'm going to put some indicator in here as well. So we have to use an indicator. And the indicator will change color to indicate the acid pH changes from acidic. So I'm going to put a few drops here of phenolphthalein. And let's add the base now and see what we get. Notice that when I add a drop, that stays around for a little while until I mix it up, and then it goes away. So the NaOH would be in this burette here, and we would be measuring more precisely, of course, exactly how much we're using. Now, what we'll find as we graph this is that the pH, if we made a graph of this process, pH versus the volume of NaOH, something that looks kind of like this. The pH starts very low. Here's 0, 7, 14. So the pH starts down here, and as we add drops, it doesn't change a whole lot. So I add a few more drops of the hydroxide, and if we had a pH meter on this, we would see that it's not changing a whole lot, just a little bit. So it's gradually going up a little bit. Now that pink around a little bit longer, the phenolphthalein turns pink in a basic solution. And as we get closer to the point where we've added enough base to neutralize the acid, the pink will start to last even longer. It stuck around a little bit longer now. So if I had a pH meter on here, that pH might be going up just a little bit more. Okay, we're almost there. And if we were doing this for real, we'd want to be very precise and add just enough, slowly add drops just till we get to the point where it neutralizes and that pink stays around. Oh, we're just about there. That pink disappeared, so we need to add maybe one more drop of the sodium hydroxide, and there we go. So once that pink is there and it stays there, we know we've reached the end point. So we've come up, and that pH starts to change much more rapidly. Now the point where phenolphthalein changes color is right about in this range, just a little bit after pH 7. So this is where our indicator changes color. Now the difference though between it not changing color and changing color, you notice, was a single drop. So that's a very accurate way to know, essentially the volume between 7, between where it changed color, was essentially the same. So the volume of NaOH we added, we can measure very, very accurately how much NaOH was needed to react with the amount of acid. How much of this base was needed to react and neutralize all of the acid. We can measure that very exactly, very precisely. Now if we were to continue this titration, and we use, say, a pH meter to record how the pH changes, if we continued to add more base, that line on the graph would go up, and then it would start to kind of level off once again around 14 for the pH of sodium hydroxide. So the process then is we measure a certain amount of sodium hydroxide, we add that until the color changes, and when the color changes, that's called the endpoint. So that's the point where we end the titration, and it shows how much acid or base we needed to react with the acid. So let's apply this now. We have a 250 milliliter sample of hydrochloric acid solution, and it's placed in a flask with a few drops of phenolphthalein. So this is the indicator. If 32.6 milliliters of a 0.185 molar sodium hydroxide solution is needed to reach the endpoint, what is the concentration and molarity of the hydrochloric acid solution? Okay, so in this we have our burette. In the burette, sodium hydroxide is known. We know the of the Na. Tells us right there it's 1 or 0.185. In a flask, we have the unknown HCl. So in the flask, we have HCl, and that's unknown. We don't know the molarity, that is. We do know its volume. We know that we have 12 milliliters. So we are adding the 32.6 of this. We're measuring it before and after. So we've measured the difference there and found that we needed 32.6 milliliters of the base. So that's the final minus initial, 25 milliliters of the acid. What the molarity then of the acid is. Example of how we can use titrations to solve these types of problems. The first thing we need, of course, is the equation. So the equation we wrote down earlier, HCl aqueous plus NaOH makes water and sodium chloride. And so that equation is balanced already. Now, we have givens and unknowns that we should list to help us solve these problems as well. So let's go back through our problem and list each thing that we have. So we'll list information for the HCl and we'll list information for NaOH. So for HCl, we have 25.0 milliliters of the solution. We have an unknown molarity though. So the molarity is unknown. Now for sodium hydroxide, I'll put that in the blue, we have the amount used, the volume, 32.6 milliliters, NaOH. Again, this is for HCl. And we also know its molarity. So that's written right here, 0.185 molar. So 0.185 molar NaOH. Now, what should we start with to solve these problems? So we know we're going to use this relationship, the relationship we saw already, that for every 1 mole of NaOH, there's 1 mole of HCl. That's our key relationship, that's our link, that's our connection, our bridge to figure out how much of one thing there is based on the amount of another. But what should we start with? We have all these numbers here. What's the starting point? Well, we're starting with the known. You always work from known to unknown. So since we know about the NaOH, we're starting with this, and we're going to figure out the molarity of the HCl given this information. Well, we have a couple of numbers here. We have the volume that we use, and we have the molarity. Which one would it be easier to start with out of those? Well, since molarity is a ratio, we can think of molarity like this. Molarity stands for moles per liter. We can interpret this number as 0.185 moles of NaOH per every 1 liter of NaOH. So since this is a ratio, it's generally easier to start with the thing that's not a ratio, and we'll use this as a conversion factor to work our way towards the rest of the solutions. So let's plan it out, map out where we're going with this problem. Here's the plan of attack. So we're going to start with the number of milliliters of NaOH. We're going to start with milliliters of NaOH. So then, once we have milliliters of NaOH, we can figure out, using this ratio, the number of moles of NaOH. So we can use the molarity to figure that out. Once we have moles of NaOH, now we can plug that into this ratio here. We can look at the mole ratio of the reaction, and we can go from moles of NaOH to moles of HCl. So it's just good old stoichiometry there, moles of NaOH to moles of HCl. And at that point, the problem wants molarity. We'll need to take those moles of HCl, we'll stop our chain calculation, and then we'll use the volume of HCl, divide by the volume, and then that will give us the molarity of HCl. So let's see what that looks like. So our first step is milliliters of NaOH. We're starting with this number right here. So we have 2.6 milliliters AOH. Now, milliliters and ratio need to be converted since we have liters on the volume of NaOH. Let's just go ahead and do that right now. We would, of course, divide by 1,000. That would move this decimal point to the left 3 places, or it would be 0.03. That decimal point goes away, and it's liters. So that's 0.0326 liters of NaOH. So we'll take that out. We'll just go straight to liters. So now that we have liters, we can go straight to the molarity. Flip that in the correct way so that we cancel out liters. That's going to bottom. So for every 0.185 mole of NaOH, there's 1 liter Na. So right now we've from liters to moles of NaOH. Next step is to go from moles of NaOH to moles of HCl. Well, we know that there's a 1-to-1 ratio based on this equation. So we'll write that ratio. For every 1 mole of NaOH, there's 1 mole of HCl. Okay, so we'll stop the conversion factors there. That will give us moles of HCl. And we can calculate that. So the number on the top comes out to be 0.00603 moles of HCl. We're not quite done. The problem wanted molarity of HCl. Now molarity, moles divided by liters. So now that we have moles of HCl, we can divide that by the volume of HCl. That was given to us right there, and that was the molarity. Now this number again was given to us in milliliters, so 25 milliliters is going to be 0.025 liters. So we take our number, solved right there, and one more step is the number of moles divided by the number of liters. So the number of moles is 0.00603 moles, and the number of liters would be this converted to liters. So again, that's 0.025 liters. 0.025 liters. We divide those numbers, and we have found that the molarity of the unknown solution is 0.241 moles per liter, or capital M, 0.241 molar. So we can see how useful this idea of a titration is. We can use a known to find out an unknown in the lab through this process. Let's look at a variation on these types of problems. We can solve for many different things. Another thing we might find is the volume. So titration to find the volume. What volume in milliliters of a 0.115 molar NaOH solution would neutralize 25.0 milliliters of 0.106 molar sulfuric acid solution? So our first step here is to write the equation. We have sulfuric acid reacting with sodium hydroxide. So our equation for that is H2SO4 aqueous plus NaOH and the neutralization reaction involves the cation from the base joining up with the anion from the acid, and so that's going to make the combination of Na and sulfate. Now sodium is a 1 plus, sulfate is a 2 minus. So when we crisscross those, we end up with Na2SO4. And so that's aqueous. And the other product is water. Now, we might need to balance some of these equations. So this one, it turns out, is not balanced. We have 2 sodiums on this side, 1 on that side. So we'll need to fix that. Also, the number of hydrogens are not balanced either, and oxygens. So if we put a 2 in front of NaOH and put a 2 in front of H2O, that should give us what we need, because now we have 2 sodiums on each side. We have a total of 6 oxygens on each side, 4 plus 2 more is 6, and then the hydrogens, we have 4 on each side. So 4 over there and 2 here plus 2 more. So now we have the balanced equation, and we can continue on. We're given information about both the sodium hydroxide and the sulfuric acid. So for the acid, we have 25 or 0.115. Okay, now in this problem, we're actually given more information about the acid. So usually we're used to getting information about the base. In this case, we actually are given the information about the acid, and we're working backwards to the base that would be in the burette. So we're given 25 milliliters of the H2SO4. So the volume of H2SO4 is 25 milliliters. And let's just go ahead and convert those to liters right now. That'd be 0.025 liters. And we're also given the molarity of the H2SO4. And so that molarity then is 0.106 molar. Now, the information about the base, the sodium hydroxide, we're given the molarity of it. So the molarity of NaOH is 0.115 molar. And we're looking for the volume of NaOH. So we want to know how much of that NaOH is needed, how much of this is needed in order to do the titration. We're working backwards. We don't usually work this way, but in this problem we're working backwards. So the plan here is we're going to start with the volume of acid this time, this single number. We'll use molarity. Then we'll go from moles of the NaOH to the volume of NaOH using the molarity again. So we have the volume of H2, the moles of HSO4. Then we can use the ratio between NaOH and H2SO4. Use this ratio here to connect the moles of H2SO4 to the moles of NaOH, and we'll find moles of NaOH, and then we can use the molarity to figure out the volume of NaOH. So our first number is the volume of H2SO4, 0.025 liters of H2SO4. Now we use the molarity. Molarity can be interpreted as 0.106 moles per every 1 liter. So for every 1 liter of H2SO4, there's 0.106 moles of H2SO4. Next, we're at moles of H2SO4. Next is the ratio. For every 1 mole of H2SO4, there's 2 moles of NaOH. So for every 1 mole, H2SO4, 2 moles NaOH. And now we can use the molarity of NaOH. It's 0.115 molar, which can be thought of as 0.115 moles per every 1 liter. So for every 0.115 moles, I flipped that conversion factor, there is 1 liter of NaOH. So it's all set up. Calculate that. We end up getting 46.1 milliliters of NaOH.